Alright, so here we are. It is Friday, and I hope that you are all having a fantastic day. Weekend is here, although it feels like every day is the weekend, but in a bad way. Alright, so we're going to be talking about complex numbers. There we go. One of those concepts that before college algebra, we should have had a good working knowledge of this. But we do spend some time at the beginning of the semester just reviewing over complex numbers. Okay? So, let me see. Alright, we might have some interesting issues today because my dog is being a bit on the crazy side. So, we'll see. Alright, so if you remember yesterday when we had something like this, if I said what's the square root of negative 16, our response was that this is not a real number. And so it just kind of threw us off a little bit and we couldn't do anything with that. That is, until we kind of do this definition here that we have with complex numbers. Okay? So what we do is that we make this definition. And we will define the square root of negative 1 to equal I. Okay? And I is what we call, this is called the imaginary unit. Okay? And in this relationship where the square root of negative 1 is equal to I, we can then turn around and say that that is because I squared is equal to negative 1. So if we stick with the real numbers, we run into this issue of not being able to have a number that we would square to get a negative. So we develop this concept of the imaginary unit so that we can, do some more stuff. And it's really bad that they call it an imaginary unit and you think imaginary numbers like they're not, like they have no use in the real world, and that's not true. These guys are useful. It's just a moniker that kind of stuck with it as an imaginary number, and that's how we tend to think of them. But we have this definition for the imaginary unit, and we're going to walk through how do we deal with these guys if we're doing adding, subtracting, multiplying, and dividing. Okay, and so that's what our focus is going to be today. So keeping this definition in mind, we can now take this radical, the square root of negative 16, and we can rewrite this to say that this is the square root of 16 times negative 1. So we can do it like that. And this just means that I have, when I split these square roots, the square root of 16 times the square root of negative 1. So the square root of 16 is 4, and the square root of negative 1, from what we have here for this definition, is going to be I. So we're going to say that the square root of negative 16 is 4I. Which means, if I were to take the square root of negative 49, first of all, we need to know that the square root of 49 is 7. Yes, ma'am. Yes, ma'am. What do you need? What is it? You be a good girl? Can you wait? Sorry about that. And then this negative factor right here is going to come out as an I, like that. So the answer here is 7I. If I do the square root of negative 25, the square root of 25 is 5, and this negative, the negative inside, gives us the factor of I on the outside like that. So 5I. So there's really not a whole lot to that. You just have to pay attention to your signs and everything else. Greetings. How are we doing this fine afternoon? Okay, if I do negative the square root of negative 144, we have two negatives here, but you need to make sure you understand that these negatives don't get to see each other. This negative is going to be done once we're done dealing with the square root. So when I deal with the square root, of course, the square root of 144 is 12. And as we keep mentioning, this negative factor, the negative inside the radical becomes I on the outside. And once you're done with that, now you get to apply this negative. So the negative is just going to be tacked on right there. So there's your negative. The square root of 144 is 12, and the square root of the negative gives us I. There we have it. But you've got to be careful and you've got to pay attention to the problem that you have in front of you. Because if I were to ask you this, I say, what is the cube root of negative 27? Now, if you're in this mindset of dealing with imaginary numbers, you might say, oh, well, this is going to be 3i. But this is where it's actually not true. The way that we defined I up above is that I is going to come from the square root of a negative number. But the cube root of a negative is something that I can do. And the cube root of a negative is a negative. So the answer is just negative 3. So please make sure you understand the difference between this problem and let's say something like this. So we take the square root of negative 27. So when I do the square root of negative 27, well, 27 is not a perfect square, so I'd be looking for factors of 27 that are perfect squares. So 27 can factor as 9 times 3. We look at the square root of each of these. So the square root of 9 is 3, and since I have the negative inside here, this negative inside is going to give me a factor of I outside the radical. And then I have the square root of 3, who's just going to be tacked on here at the end, because you can't do anything with that guy. So this is a much better way to write it. I know that technically you could say that this is 3 squares of 3 and put an I at the end, but we don't really want to do that because oftentimes when we do our radical sign, I've seen students go a little bit too far with that, and they end up putting the I inside the radical. So to avoid confusion, we write it like this. This is a much better way of doing it. Now, I want us to look at this again, just to make sure we understand where everything is coming from and where everything goes. So if I break this down all the way, the 27 breaks down as 9 times 3, and then you have a negative 1 as a factor. When you separate this using that product rule for radicals, you have the square root of 9 times the square root of 3 times the square root of negative 1. Okay, so the square root of 9 is just 3. The square root of negative 1 is your factor of I right there. And the square root of 3, well, we didn't do anything with that, so he just comes down here as the square root of 3. That way you see exactly where each factor comes from in our final answer. I don't want there to be a mystery about any of this. Okay? So let's do another one. If I have negative the square root of negative 200. Okay. So the negative is the negative, right? It's just going to be out there. So I'm not going to address that guy until I take care of whatever the radical gives me. Okay. So if you want to, you could go ahead and say this is equal to negative, just bring that guy straight down. When I look at the square root of 200, I know that 200 can simplify, can break down as 100 times 2. Now, that's not the only way to break it down so that you can simplify something out of the radical, but it is the best way of doing it because this is the largest perfect square factor that we have for 200. Okay, so the square root of 100 is 10. The negative factor that's inside here is going to come out as an I, so this is negative 10I, and then the only piece that was not spoken for was the 2, and so that is the piece that stays inside the radical. And there we go. So in order to simplify these guys, we still need to know how to do the material that we talked about yesterday, which was just simplifying radical expressions. Because if we can't simplify the square root of 200 by itself, then we're not going to get any further with the square root of negative 200. All right. So that's the basic idea for complex numbers, for the I. But let's talk about complex numbers in general. What do they look like? All right, so most complex numbers are going to take on the form a plus bi. They're made up of two components. They are made up of a, which is the real part, and then you have b, you have the piece that is connected to the imaginary unit, and this is called naturally the imaginary part. So an example of a complex number would be something like 3 plus 5i. You've got your real part and you have your imaginary part. Now, typically when we talk about where do numbers go, we would look at a number line, which is just going to be a single dimension, right? It's just left and right on the number line, plot your number, fill in the point, and you move on. For something like a complex number, we talk about graphing these guys as points on the complex plane, where instead of having x, this is called the real axis, and the y-axis is now the axis for your imaginary part. So if I want to look at plotting 3 plus 5i, that's 3 in the real direction, 5 in the imaginary direction, and you would just line it up like that. And so this is the number 3 plus 5i. Okay? Really, you're kind of looking at that as an ordered pair. 3 for the x, 5 for the y, and you mark your point. Another way of seeing this and making connections to physics and other real-world examples is that you think about that connection from the origin to this point. You can think about this like a vector. Okay. Now, the distance from here to here is something that we can calculate because earlier on we talked about finding the distance formula at the beginning of, or I guess at the beginning of the second unit. We're talking about the distance formula from one point to the next. And you can find that and calculate that by using the Pythagorean theorem. And so that gives you what's called the magnitude of this number. It's basically the length of that. And that's useful for a lot of other applications when it comes to imaginary numbers. If I needed to find the square root of this, I would first need to know what is that distance from the origin to that point. Now, finding the square root of an imaginary number is a concept that you're going to talk about in either trigonometry or pre-calculus. So right now, we're just going to leave that alone. But anyway, this is what a complex number looks like. There's really nothing to do here. What we do want to do is we want to look at the 4 basic operators for math: addition, subtraction, multiplication, and addition. That's what we're going to look at today. It's pretty simple to do this stuff. So in order to add complex numbers, all you need to do is combine like terms. To add complex numbers, combine like terms. For example, let me take that 3 plus 5i that I wrote above, and let me add to that 7 minus 2i. If you were to look in a textbook, a lot of times they try to give you a formula for doing this, but there's no formula that you need. It's just a matter of combining like terms. So you combine the real stuff, so you have 3 and a positive 7, so that gives me 10. Then you look at your imaginary pieces. You have a positive 5i, and you have minus 2i. So positive 5 and negative 2 is going to give you a positive 3i. What we need to remember here is that taking something like 5i minus 2i to get 3i is no different from taking 5x minus 2x and getting 3x. It's the same idea, it's the same concept. So we don't need to overexert ourselves, just make your life easy. And in a little bit I can show you how you can use the calculator to do some of this stuff, but again, you don't need a calculator. But if we want to check things, we can totally do that. So if I have negative 6i minus 5i plus 2i minus 9i. All right, we're adding. So all we need to do is combine like terms. And I don't even know what's going on here. I don't even know what I'm doing in my mind. I've got eyes everywhere. So this is not really the problem that I meant to do. So I'm just going to change this up real quick. I mean, I don't think anybody's going to be really upset about that. So we can just pretend this didn't happen. We can just, that's great. Love it when the whiteout tape doesn't work. Unless I've somehow reached the end. There we go. You saw nothing. That's what I meant to write. I guess I'm just having a case of the Fridays. So if I want to combine these, negative 6 and a positive 2 gives me negative 4. And then negative 5i and a negative 9i gives me negative 14i. And that's it. You combine the real, you combine the imaginary parts, and you move on. Subtraction is pretty much the same thing. You're still looking for like terms, but you have this extra piece of subtraction that you have to worry about. So if I take 4 plus 7i minus 10 minus 4i like this. The best thing for us to do is to take this negative and distribute that. So if I take the negative and distribute and break these guys out of the parentheses, it becomes just another addition or combining like terms problem that we just had. So when I rewrite this, I get 4 plus 7i. The negative is going to distribute, so we get negative 10 plus 4i, like that. And just combine these guys, right? So 4 and a negative 10 gives me negative 6. For the imaginary pieces, we have plus 7i plus 4i, so that's plus 11i. And yet again, we are done very, very quickly. Not a whole lot that we have to do. We just have to pay attention to our signs, and we're going to be all right. Even when it seems like all hope is lost. Negative 5 plus 4i minus negative 12 plus 3i minus 10 plus 19i. Well, we've got a bunch of negatives going on here, but we're going to be okay. We're going to take this negative right here, just like we did above, and we're going to distribute to that complex number. And then we're going to take this negative here, and distribute that to the 10 minus 19i. Alright, so let's write this. I'm going to rewrite this. This is still just negative 5 plus 4i. This now becomes a plus 12 and minus 3i. Distribute here, we have negative 10 minus 19i. So we have 6 terms, but it's still just a matter of combining like terms. So when I combine, I've got negative 5 plus 12, which is positive 7 minus 10 is negative 3. For the imaginary pieces, 4i minus 3i is positive I, so a positive 1 and a negative 19i will give us negative 18i, like that. Now, real quickly, I just want to jump over here, and I want us to use the graphing calculator so we can see a few things. So if I take the example that I have right here, I can type this into the graphing calculator, even with the i's, to get an answer. Now what you need to understand is that your I is going to be right here above the decimal. If you press the second key and the decimal, that's going to give you the I. So I can type this in exactly as I see it. So parentheses, and now see that leads off with a negative, so if you do the minus sign, it's going to be wrong. So it's going to be negative, use the negative, 6 minus 5i. Again, please make sure you note the difference between a negative when you're trying to write that as a lead-off negative versus the subtraction sign. And then we have plus, parentheses, 2 minus 9i. When you hit enter, we see that we get the answer that we already have here, negative 4 minus 14i. Even this last problem that we have. So we have negative 5 plus 4 second decimal to give me the I. Then we had minus, see that was negative 12 plus 3i. So in parentheses, negative 12 plus 3i. Minus, and then we had 10 plus 19i. 10 plus 19 second decimal for the I. And yeah, everything checks out. Negative 3 minus 18i. So you see that we're working with imaginary numbers right here in the calculator, but watch this. If I go to do a square root, so second square button to get the square root, and I type in negative 25, it's going to yell at me and say this is a non-real answer, even though it was just doing operations with non-real numbers before. So here's how you can fix this. Then you need to do this every time that your calculator gets reset. So let's quit out of this. If you go to your mode, if you scroll down here, it says real, and then it says a plus bi, which is that standard form for a complex number. When I hit enter, I'm now going to be in complex mode. Now that doesn't really affect us too much if we're doing normal operations, but it now allows us to do things like the square root of negative 25 and get an answer like 5i, which we were not able to get before. If I do negative times the square root of negative 81, so the square root of 81 is 9, the negative inside gives us 9i, and the negative outside just makes everything negative. So the answer should be negative 9i. And there we go. So if you know how to use the calculator, you can use it to your advantage, but don't abuse that power. Remember, with great power comes great tax write-offs or something. I don't know. So we'll come back to that guy here in a moment. The next thing we want to look at is multiplying complex numbers. If you know me, you know that multiplication is super fun. So we're multiplying complex numbers. So imagine if I were to take something like this, 5 times 2i. You just multiply like you would normally. And the big thing about all of this is that you need to remember that I is just like the variable x, and so treat it that way. So 5 times 2i is just going to be 10i. And we're done. There's nothing else to do. If I do 7 times 3 minus 4i, well, now we have a distributing problem. We need to take the 7, and we're going to distribute, just like we would do for any other multiplication problem that looks like this. 7 times 3 is 21. 7 times negative 4i is negative 28i. How can things possibly get bad, right? Well, that's when we take something like this. If I take 5i times 6i. So we're multiplying 5i times 6i. Think about this as though they were x's. What would you have? What would you see? So, off to the side, I want you to imagine that these are x's instead of i's. And if we do that, of course 5 times 6 is 30. And then you have x times x, which gives us x squared. So why would we expect things to be any different here? This is all multiplication, so I can rearrange things the way I want to. I can rearrange my factors to give me something that makes a little more sense. So 5 times 6 is 30. I times I is going to give us I squared, just like that. Now I would say that's it, we're done, we can move on. However, we do not leave I squared. You're never going to leave a power of I higher than to the first power. Now on the first page of notes today we said how I squared is actually negative 1. So this means 30 times I squared means times negative 1, which then equals negative 30. So this is the correct answer. And here's the crazy thing. We just multiplied two imaginary or complex numbers, and we got a real number. We got negative 30 out of this. So that's the thing we need to keep in mind. Anytime we see I squared, it's going to change the sign of the term that it's connected to. So if I have negative 7i times 2i, if I multiply these straight across, that's negative 14 for the coefficient. I times I is I squared. But we said that this I squared gives me a factor of negative 1. And it's very important that we understand it's a factor of negative 1. It's not adding and subtracting. It's multiplication. So it's going to change the sign. Instead of having negative 14, we're going to have positive 14 for that product. Right, exactly. Well, now that we have the little stuff out of the way, then we go for the big stuff, right? Let's take 8i times 3 plus 7i. Oh, I'm sorry, girl. I didn't mean to mess you up. All right, so what would we have here? For your first step, what do we need to do? You okay, girl? Can't tell if my dog is tired or... No, yeah, she's tired. Or hot. She's learning something. She's been getting in these moods every day whenever I'm done streaming because she knows it's time to go for a walk. And she loves that. So if I don't end the stream at the right time, she's going to start clawing my leg until I finally take her out. So I have to move pretty fast here. So here, Yeah, it is cute until you start bleeding. But I still love you, isn't that right, girl? Alright, well, whatever. So here, 8i times 3 is 24i, and then 8i times 7i is 56i squared. Remember, we can't leave I squared. So what I like to do is I like to circle the entire term like this. Circle the whole guy, and I arrow off to the side to say what he becomes. So a positive 56i squared becomes negative 56. Remember, the I squared just changes your sign. And when we write our answer with the real part first, so negative 56, followed by the imaginary part, 24i. Okay? Does it seem to be too bad? Until we do something like this. So if I take 2 plus 5i times 7 minus 3i, we remember our multiplication of polynomials from a long time ago. All we need to do here is FOIL, right? We were even doing some of this yesterday. So let's FOIL this. Let's take the 2 and distribute. So we can try to color code this so you can see where everything goes. Sure, use the right colors. All right, so I'm going to distribute the 2 here. So we have 2 times 7, which is 14. 2 times negative 3i is negative 6i. And then we're going to take the 5i and distribute that as well. So that's plus 35i, and then we get a negative 15i squared. Piece by piece, match the colors, everything's going to be fine. One of the things that students often miss is when they do 5i times 3i, they forget that it's I times I, which is going to give you I squared. So you have been warned. But since I have I squared, what's going to happen to this negative 15i squared term? What is that I squared going to do to the negative 15? It's going to give us a negative times the negative that's already there, which is going to give you a positive 15. Again, paying attention to our signs. And now we rearrange and we combine like terms. So put all the real stuff together. We've got 14 plus 15. That gives me 29. And negative 6i plus 35i is positive 29i. And that's it. I think we can fit one more of these guys here on the page. Let me try to create a bit of separation here. All right, so I'm going to take 5 plus 3i times 7 plus 6i. And really, there's no difference between this problem and the problem that we had above, except for the fact that the numbers are different. Maybe slightly different signs, but it's no big deal. Okay, so let's distribute just like we did above. Distribute the 5, and we'll distribute the 3i as well. All right, so 5 times 7 is 35. 5 times 6i is plus 30i. Now distribute the 3i, so we get a plus. 3 times 7 is 21, so 21i. 3 times 6 is 18. So 18, don't forget that this is I times I, which gives us I squared. And we know that every time we have something that's squared, that's an I squared, we're going to circle that term, and we're going to say what it becomes. So plus 18i squared, once you activate the power of the I squared, gives us negative 18. So now our real parts include the 35 minus 18, so that's 17, and the imaginary pieces, positive 30i plus 21i is positive 50i 1i, like that. And we're done. Now, if you check this on your calculator, I just want you guys to see that everything checks out, that I'm not making it up. If I do, let's see, we have parentheses, 5 plus 3i times 7 plus 6i. Again, the calculator can just give you the answer. And for some of the stuff we're going to be seeing once class resumes, you want to make sure you have something like this on hand just to help you out. It's not mandatory, but yes, I'm still here, girl. Yeah, it's not mandatory, but it is helpful. And there we go. 17 plus 51. I. Do you need something? Just tell me what you need. Oh, she is spoiled. Very, very spoiled. Isn't that right, girl? You do know there are 3 other people in this house that you can talk to, right? I guess I just happen to be her favorite. She gets jealous of me. If my wife and I are hugging, she tries to separate us. And what are you going to do? Oh, excuse you. Goodness. All right. If I take 5 plus 5 plus 7i times 5 minus 7i. That's not me. Oh, my word. Okay, so let's FOIL this just like we were doing before. When we FOIL, 5 times 5 is 25. 5 times negative 7i is negative 35i. On the inside, we get a plus 35i. And the product of the last 2 terms is negative 49i squared. Okay? So, let's see what we can do. Just like the last problems, minus 49i squared becomes plus 49. So we combine 25 and 49 to give us 74. But look at the imaginary pieces. Minus 35i plus 35i, these guys are additive inverses and they just go away. They become 0. So the answer now is just 74. Yep, gone. Adios. No está aquí. I don't know why I use that voice. It's either that or something that's like deep. Like a no está aquí. Still working on the Spanish. Anyway, let's talk about why this is. This is one of those neat special products that we have. A plus bi times a minus bi. Okay. If we look at it in its pure form, and what we have here are what we call complex conjugates. Okay. So these guys are complex conjugates. Now, if you remember when we were multiplying conjugates before, like just normal conjugates, we would end up with a difference of 2 squares. We would say a squared minus bi squared. And if we work this out, that's a squared minus b squared I squared. But we've just gone through a whole page talking about what happens when you have this I squared. So this minus b squared I squared is going to become plus b squared. And so what we end up here is we just have the sum of squares. we were talking about factoring earlier this week, we said that when you have the sum of squares, it doesn't factor using real numbers, but it can factor using complex numbers. And so, bless you. And so that is the little formula that we have. You want to get up here again? Yeah. Oh, gosh. Why don't you have somebody else take you out? Go for a walk. So anytime you have something that is the product of complex conjugates, a plus bi times a minus bi, you can't have the pen. No, these are teacher pens. You're not a teacher. You got to wait your turn. Oh my word. Yeah, you get it. What she's actually chewing was part of a toy that she got for Christmas, which was like a Thor's hammer from Marvel, but the actual hammer part was the soft, squishy stuff with the stuffing. So she ripped that open within a few minutes. So we had to trash that. So she just has the handle that she's playing with now. Okay, so here is that fantastic shortcut that we're going to be using. The sum of squares. We don't have to go through this whole process. Don't do that. Don't FOIL. Use the special product. So that when we have, here we go. When I do something like this, if I do 3 plus 4i times 3 minus 4i, as long as these guys are conjugates, in this case complex conjugates, the product is going to be the real part squared plus the imaginary part squared. There's not going to be any i's here in this product because the I squared activated its negative with this negative giving you a positive. And look here, there's nothing imaginary. The a and the b are just the real and the imaginary parts. No imaginary units. And so we just work this out. So 9 plus 16 is 25. Okay, that's it. If I take 7 minus 11i times 7 plus 11i, these guys are also complex conjugates, so I can use the shortcut. The shortcut says square the real part, square the imaginary part, the coefficient for the imaginary term there, and add those guys together. That's all we have to do. Do not make it more complicated. So 7 squared is 49, and 11 squared is 121. So 49 and 121 is 170. Okay? Now this is where students can easily get tricked. If I say 8 plus I times 8 minus I, something always bad happens here. Must you? Okay. This is what happens whenever you go live. Okay, you're good. Chew the bone, not the table. So when I work this out, I take the real part squared, so that's 8 squared, plus, now the trick here is what you say is the imaginary part. See, a lot of students would take the I and try to write I squared, but it's not I squared. We need to remember that this is understood to have a coefficient of 1. And so the imaginary part is the coefficient 1. And now that we have that, we can easily say 64 plus 1, and that gives me 65. Okay, what do you guys think? Should be pretty simple, right? Same stuff that we did in class earlier this semester. Just making sure that we understand this, because we're going to be seeing this stuff as soon as we come back from our very extended break. This is part of the stuff that I've been working on, and I'll be having it up for you guys hopefully sometime next week, so you can go ahead and start looking at it and get started. So there are going to be videos, there's going to be some guided notes for you, just to kind of help you along as we make our transition to full-on online instruction. So, hoping for the best. All right. Yeah, you know what? I'm with you too. I like the face-to-face. It's what works best for me. That way I can read your faces and understand what's going on. So we're going to have trying to have a lot of virtual office hours for you guys. And still, I think I know how I want that to work. I don't know if I need to do it for everybody or just say different groups meet on different times. But we're going to work it out. And I think when you look at the notes that I have, the notes I'll have for you is going to be the same stuff that we do in class, except you'll be able to have those notes in front of you while you're watching a video, so you can see a lot of the instruction, a lot of the words I'm going to be saying, and then you have examples. So there's going to be an example with a bunch of blank space, so that you can have those notes, print them out, and just fill in the blanks there, fill in the big gaps as we work the problems. I mean, you don't have to print them out if you don't have the capabilities of doing that, so you can just copy them on your own. But those notes are going to be there, along with the problems that we're going to do with the videos. Again, I'm hoping this works out. This is just what has been kind of forced on us, and we're going to make the best of it. All right, so let's look at dividing complex numbers. Now, for the most part, this isn't too terribly bad. If I take something like, I don't know, say 14i divided by 2, it should be pretty straightforward. If you think about the I just like a variable, then the only thing you can simplify is the 14 over 2. So we get 7, and then the I just comes along for the fun of it, right? Nothing else to worry about. If I have 20i divided by 5i, as long as we remember that there is multiplication going on between the 20 and the I and the 5 and the I, we're going to be okay. Because these i's are now common factors that can reduce away. So we're left with 20 over 5, which just becomes 4. And that's it. Right? And everybody's happy. Where things get a little bit more complicated for us is when we end up with I in the denominator, but no I in the numerator where we can reduce it. So if I have 35 over 7i. See, if I didn't have the I here, 35 divided by 7, nice and easy, you just get 5. But with the I, it throws us off. So what we do is we make a slight correction here. And I feel the easiest way to make that correction is to multiply the numerator and denominator by a factor of I. Right? So I over I equates to being 1. And we know that if we multiply something times 1, it doesn't change its meaning. It may change the way it looks, but its meaning is still the same. So when I work this out, I get 35i, and you might be saying, why are you making it worse on the top and worse on the bottom? Well, when you multiply 7i times I, you get 7i squared. And we've just spent a fair amount of time talking about what happens when you have I squared. So 7i squared now becomes negative 7, and now you don't have anything imaginary in the denominator. So that you can finish this problem, 35 divided by negative 7 is negative 5, and the I that's in the numerator is this I right here. So we just have to make a slight correction. That's all. If I take a bigger complex number, say 15 plus 25i, and I want to divide this by 5. To work this out, it's nothing more than other fractions that we've had, where when you were dividing by a single piece, if your denominator is just a single term, you can split the numerator, and you can say 15 over 5 plus, and then you can write the other term, 25i over 5. Okay? See, we're so used to saying if we have the same denominator, we can combine this into a single fraction. And now what we're doing is that we're saying, you know what, you did combine into 1, let's break it apart. So 15 divided by 5 is 3, and 25i over 5 is 5i. So again, as long as we're dividing by real numbers, we really shouldn't have a problem. However, if I say 24 minus 16i divided by 6i. Again, I'm just dividing by a single term, so I want to take the binomial that I have in the numerator and I want to split it up into two smaller fractions and see how I can simplify those. So 24 divided by 6i minus, and this is 16i divided by 6i. So you don't have to look at this as one whole complete problem. You can look at it as two smaller problems to simplify. Now, this guy's going to be nice enough because these i's are going to reduce. However, this guy has an I in the denominator, and I don't like that. And there's no I in the numerator for him to reduce with. So I'm going to put in the missing factor here of I in both the numerator and denominator. So this gives me 24i divided by. Now, if you're paying attention to what we're doing, you understand the reason behind each step. The reason we wanted to multiply this times I is so that this whole guy becomes 6i squared, right? When this becomes 6i squared, it's going to end up giving us negative 6. So we get to rewrite this without any imaginary pieces now. And then over here, this is minus 16 over 6. All right, so as we simplify, 24 over negative 6 is negative 4, and there's the I. We reduce 16 over 6. So 6 doesn't go into that evenly, but we can at least reduce this by the common factor of 2. And we get 8/3. Now you might think, okay, this is good enough for me, I can move along. We really want to write this with the real part first. So negative 8/3 minus 4i is the better way of writing that. And now I'm going to show you what this looks like in your calculator in case you're trying to check to see if things are working out okay. Maybe you're working on some homework or you're just making up some problems to see if you can do the problems that you make. But you've got to make sure you type things into the calculator correctly. Okay. So, if I'm typing this in, we need to understand that this whole piece is the numerator. If you just go 24 minus 16i divided by 6i, you get that number. That's not even close. What you meant to do, what you should have done, is taken 24 minus 16i, and you want to put that in parentheses because you have that whole group that is being divided by 6i. Okay? But again, here's another issue where you have to pay attention. If I say divided by 6i like this, now I've got a decimal here, so let me go ahead and convert that to a fraction by pressing math, hitting enter to convert to a fraction. I get 8/3 plus 4i. Now that's awfully close to what I have here, but we're off by a sign. And the reason that we're off by a sign is because when I did this division up here, the calculator does not see this as dividing by 6i. It sees it as dividing by 6, finish that, and then multiplying the result times I. That's not what we want to do. we want to make sure that the 6i is completely in the denominator. So we need to do 24 minus 16i divided by, use parentheses again for that denominator, 6i. And again, let's convert this to a fraction by pressing math, converting that to a fraction. And there we get negative 8/3 minus 4i, which is what we have right here. So if you're checking with the calculator, you have to make sure that you are checking correctly, that you are typing things in the way you're supposed to. All right, well, that's all well and good, but our denominators are not always so nice. Okay? Sometimes our denominators contain binomials, and we have to address those in a slightly different way. So if I take 5 divided by 3 plus 2i, your denominator is a binomial, and you are not allowed to split your denominator. You can't split this into two fractions. We do need to somehow find a way of getting rid of the imaginary number down here. And just using an I is not going to work. Instead, we are going to have to use the conjugate of this denominator. So we're going to have to use 3 minus 2i in both the numerator and denominator. Okay. By using 3 minus 2i, we have the product of conjugates, which is what we just got done talking about. This product of conjugates is going to give us 3 squared plus 2 squared, right? And you might say, what happened to the I? Well, that was that whole special product about how the product of complex conjugates gives us the sum of the 2 squares, squaring the 3 and squaring the imaginary coefficient there, 2. So we work this out, and that's 9 plus 4, which equals 13. So all of this is now going to be my denominator, 13. In the numerator, we have 5 times 3 minus 2i. Now if I write it like this, if I keep that in parentheses, so do 5 times 3 minus 2i, I'm not multiplying this out just yet, and the reason is because sometimes the numerator that you had will simplify with this denominator. The 5 and 13 don't have anything in common, so I'm now going to multiply this out. So I have 15 minus 10i all divided by 13. Now, I don't like the way that's written. I like to clearly see my real part versus my imaginary part. So I'm now going to separate this since my denominator is a single term. And I'm going to say 15 over 13 minus, and this becomes 10 over 13i. And there we go. Shouldn't be too bad. We just have to pay attention to our signs and make sure we remember the special product. If I have 18 over, let's do 5 minus I. In order for me to rewrite this so that I don't have imaginary pieces in the denominator, I have to use something that's imaginary, which is going to be the conjugate of the denominator. So I'll multiply times 5 plus I in both the denominator and the numerator, like that. All right, so here in my denominator, we do that special product. Okay, guess I should be using red to match what I had above. So it's going to be 5 squared plus, and again, we just talked about this, so you have to pay attention. Even though this says I, you're only taking its coefficient, which is 1. So 1 squared. All right, so let's work this out. We get 25 plus 1, so our denominator is now equal to 26. So all of this is over 26. And let's do this just like we did the first problem. Keep the 18 factored out in front. And before you distribute, see if you can reduce anything. See, above, we had 5 and 13, and these guys didn't have any common factors. So we could just distribute the 5 and then separate to get our nice numbers. Here, 18 and 26 do have a common factor. They have a common factor of 2, so I can reduce. This becomes 9, and this becomes 13. And so now I'm going to distribute. 9 times 5 is 45. 9 times I is 9i. And everything's divided by 13. And again, you want to make sure that you finish writing this in the good way. So 45 over 13 plus, that's not what I wanted to write. So I like to write mine just a little bit differently. So 9 over 13 I. Now you saw me use some whiteout because I didn't want to have I in the numerator. I like writing it like this because it's easier for you to see that 9/13 is the imaginary part. I just like to clearly write the coefficient. But that might just be me. Of course, if you guys know me, you know I like to have things done a certain way. You back for more? Of course. So let's try this. Let's do 2 plus 7i divided by 3 minus 4i, like this. Now the numerator is a little bit bigger, but so what? It's hard for me to say they're just numbers, but really, it's still just numbers. You know what you need to do. Like, you know what your step is. I don't want you to be so concerned with what's going to happen. I want you to focus on what's actually happening right now. So right now, my problem is that I have a complex denominator. Now, please do not think that these i's get to reduce because they're not common factors for the numerator and denominator. Instead, we're going to use complex conjugates, and I'm focusing on my denominator, so 3 plus 4i. And 3 plus 4i in the numerator as well. Having these guys in place means I get to use that special product, so that's 3 squared plus 4 squared, just crunching the numbers. We get 9 plus 16, and that equals 25. All right, seems okay. Now though, we have to take care of that numerator. And that numerator has the potential to get kind of ugly because we have to multiply these two guys together. We got to multiply these two binomial complex numbers together. So let's distribute. Let's FOIL. We know how to do this, right? And here's the thing. If I just gave you that problem and I said, hey, let's work that out, you should say, okay, not a problem. So 2 times 3 is 6. On the outside, 2 times 4i is 8i. On the inside, 7i times 3 is 21i. And on the last part of the product, 7 times 4 is 28. I times I is I squared. Of course, we know what to do with positive 28i squared. He's connected to I squared, and that becomes a minus 28. Okay, so still, just focus on that numerator, and let's see what we have. 6 and negative 28 is negative 22. 8i plus 21i is a positive 29i. And this is all divided by 25. And so now we finish separating things. So negative 22 over 25 plus 29 over 25i. Okay? So what I need you to understand here is that this first step was going to happen no matter what that numerator was. The denominator dictated that we needed to use the complex conjugate. The complex conjugate follows the special product, the sum of squares, to give you 25. Once we had that, we then focused on the numerator, we FOILed, we simplified, and then we could simplify. Finish separating the real from the imaginary. And let's go to our graphing calculus to check and verify what we have. So remember to use your parentheses very carefully. So I have the entire group, 2 plus 7i, is being divided by the whole group. So I need to use parentheses, 3 minus 4i. If you don't have parentheses, we know that's going to mean a completely different problem, an entirely different answer. Again, I get decimals, but as long as the decimals are, as long as they're rational numbers, then I can convert them to fractions by pressing math, convert to a fraction, and there we go, which matches up with our answer, negative 22 over 25 plus 29 over 25i. Everything works out. If we look at the problem that we did before this one, 18 over 5 minus I. So 18, now 18 doesn't need to be in parentheses because it's just that single term. If you want to put it in parentheses, it's going to be fine. Okay, no one's going to get mad at you. Dividing by parentheses, because of the group, 5 minus I. Crazy decimals, right? But remember what we said. You can press math. Right, whoops. Gotta find the right spot for this. Press math, convert that to a fraction, and we get 45 over 13 plus 9 over 13i. Okay, so there we go. We've used the calculator to verify that our answers are correct. And what I was saying about converting to a fraction, here's an example where you can't convert to a fraction. If I were to do the square root of 3, which is about 1.732. This is a crazy decimal, and the decimal representation is never going to stop. It's never going to repeat. There's never a pattern to that. So if I try to convert this guy to a fraction, nothing happens because it's an irrational number. So when we talk about rational numbers, these are numbers whose decimal representations either come to an end, where it's just zeros the rest of the way, or it has a pattern. So if I look at something like even 2 divided by 7, which is 0.285714, 285714 over and over and over again, right? That is a rational number. Most of your irrational numbers that you're going to see are going to come from square roots. So earlier today when I had the square root of 200, okay, that's what the decimal looks like. But beyond the calculator, this decimal is going to keep on going and going without any pattern, without any repetition. So if I try to convert this guy to a decimal, or excuse me, to a fraction, he's going to say, I can't. Because you can't convert that guy to a fraction. Okay. And that whole difference between rational and irrational numbers will play a very important part for the first week of material that we see, first couple of weeks of material that we see once we come back from our extended break. So that's the end of our discussion for complex numbers. I want to thank you guys for stopping by. Thank you for being there in the chat, for the encouragement, and I hope to see you guys again. So just keep in mind that next week I'm still going to be streaming here at 3 o'clock here on twitch.tv/mathman1024, and then I will be uploading these videos to my YouTube channel, which is again mathman1024. Next week, on Monday and Tuesday, we're going to be reviewing quadratic equations. How do we solve them by factoring? How do we solve them using the square root property? And then we have completing the square and the quadratic formula. I hope you have a good weekend too. Also next week, we're going to look at solving rational equations, those big nasty fractions, solving radical equations, those equations that contain square roots, cube roots, and other higher order weird things, and solving things that are quadratic in nature. And we'll finish off next week by reviewing inequalities and absolute value equations. So, hope to see you then. Have a good weekend.